Imagine you have a dataset with 20 variables. Some measure almost the same thing, some are strongly related, and together they make the data difficult to understand. Principal Component Analysis, or PCA, helps simplify that mess. PCA takes many related variables and compresses them into a smaller number of new variables called principal components. The goal is to keep as much useful information as possible while reducing the number of dimensions. Suppose we're analyzing houses. We have square footage, bedrooms, bathrooms, total rooms, garage size, and lot size. Many of these variables are related. Larger houses usually have more rooms, bedrooms, and bathrooms. PCA may combine those measurements into one component representing something like overall house size. A second component might capture another pattern, such as outdoor space compared with indoor space. The first principal component captures the greatest amount of variation in the data. The second captures the next greatest amount while measuring a different direction. The third captures the next amount, and so on. Think of it like taking a picture of a three-dimensional object. From the wrong angle, it may look confusing, but from the right angle, you can see most of its structure in a simpler image. PCA tries to find the best angle for your data. Why use it? First, PCA simplifies large datasets. 50 variables may be reduced to 5 components that preserve most of the information. Second, it helps with visualization. We cannot easily plot 50 dimensions, but we can plot 2 principal components and look for clusters, patterns, or unusual observations. Third, PCA removes redundancy. If several variables contain similar information, PCA combines their shared pattern. It can also make some statistical models faster and reduce problems caused by highly correlated variables. Before running PCA, variables are usually standardized. This matters because dollars, percentages, years, and units may be measured on very different scales. PCA then creates weighted combinations of the original variables and ranks them by how much variation they explain. Suppose the first component explains 60% of the variation, and the second explains 25%. Together, they preserve 85% of the dataset structure using only 2 dimensions. The main drawback is interpretation. A principal component may combine several variables, so it may not have a simple real-world meaning. PCA also assumes that the directions with the most variation are the most useful, which is not always true. The easiest way to remember PCA is this. Take many related variables, find their strongest shared patterns, and represent them with fewer dimensions. PCA does not keep every detail. It compresses the data while trying to preserve the most important structure.